So basically what you have here is a detector with 0 BSM falses.
Yes.
0 BSM falses. I've been asking you this over and over. It's still hard for me to believe.
Well, it's been kind of hard. It's been hard not spilling the beans over the last couple of years.
Hey, what's up, guys? So I am here at SEMA again, back with John, and this has got to be the coolest thing I have ever seen happen to radar detectors. Like, I've been sitting here all day, just pretty much hanging out here at Radenso, checking out what you guys are doing, and I guess without further ado, what are you guys revealing here at the show?
So, like you guys, I've been a radar detector user for a long time, and I'm not going to bother rehashing all of the problems with existing detectors, false alerts, filters, city mode, all this stuff. But when we sat down and moved our engineering to the USA, we wanted to make sure we were taking a fresh look at the problem. And we tried to create a from-the-scratch solution without really getting stuck in the past or past things we all assumed. Throw all our assumptions out the window and say, what's the best outcome? What's the dream? And then when that was established, we said, we know what our dream is, let's build it. And where that led us, we didn't always know at the time, but it came down to be a from-the-scratch radar detector that we engineered right in Cincinnati. And then the really cool part is that we use artificial intelligence to do all of our, I don't want to call it filtering, but our signal classification or discrimination. So this is not a radar detector like traditional radar detectors are that just look for energy over time and beep or don't. Our detector, our artificial intelligence, we call her Ray. Ray is actually looking at the signals, and just like I can look at you and I know the difference between you and another friend visually, that is how Ray treats radar signals.
So basically Ray can take a look at different signals, whether it's a radar gun, a door opener, a blind spot, and just instantly recognize what it is and then choose to alert or not.
We don't need to do city mode or low speed muting or anything like that. Why this benefits us that like using radar detectors is we've completely eliminated BSM false alerts.
Completely eliminated BSM.
Without any kind of hit and range. And in fact, using AI's filtering, it happens so quickly that we gain some additional range on the software side of things.
So basically what you have here is a detector with 0 BSM falses.
Yes.
0 BSM falses. I've been asking you this over and over. It's still hard for me to believe.
Well, it's been kind of hard. It's been hard not spilling the beans over the last couple of years. And I've tried to drop some hints here and there on RD Forum where I've said, guys, this problem is solvable. But from somebody's standpoint, it's a company telling them it's solvable. That doesn't mean anything until we actually do it, right?
So, well, actually, I know you've got some demos set up, so let's actually go check out Ray in action.
So you guys have probably heard me mention a few times how BSMs do not really look like CW. I think I've even said that this shouldn't be a problem. This should be easy to filter out BSMs. I know that we did a video in the past taking a look at what a BSM looked like, and we're going to be doing a lot more of that in the future to show you guys what it really is. And I think this is a perfect example. This is a Cadillac BSM from an Escalade. Everybody knows this BSM is one of the worst, right? It's got to be what, this and Mazda probably?
Cadillacs, they false a ton of stuff, yeah.
So I'm going to show you what it looks like, then later what CW looks like, and why artificial intelligence, why Ray can tell.
So CW, continuous wave.
Exactly. CW is continuous and BSMs are modulated. So this signal actually contains a ton of information. There's a lot going on here. So you're going to see 3 things that look to dumb radar detectors, legacy detectors, like CW carriers, and that's these here. But they're not really. They're pulsed on and off, they're different frequency, and then the signal goes away. There's nothing here. And then it's going to come back in a second. Yep.
There it goes.
And all of a sudden it sweeps back. So you can look at this and you can kind of remember what it looks like. It's funny, after I've been doing this for a while, I find myself driving down the highway and I kind of see the pictures of what the car's BSM emitters look like in my head. I'm like, oh, like that's a GM emitter. Oh, that's a Mazda emitter.
How is this different than like a police radar gun though?
So a police radar gun, which we'll take an even better look at in a second, is just one line.
Just one big spike.
It's one big spike. And that's because it's not sweeping in frequency, which on this chart is left and right.
Okay.
And it's not turned on and off or pulse modulated. It's just continuously on. That's why we call it a CW emitter.
But this is like, if you look at it, it's really obvious. Why do so many other radar detectors false when we can look at it and it's like clearly not police radar?
Yeah. So I mean, traditional radar detectors are not police detectors. They simply say, is a certain amount of energy present within the bands that we care about, KA or K bands, yes or no. And I'll actually show you why GM false alerts that style detector. So I want you to watch right here. Do you see these 3 spikes? It's turning on the emitter and it's powerful enough where this looks like 3 individual CW carriers.
It looks like a bunch of K-band right there at that frequency range.
Now, the reason that the Cadillac false is less strong than Mazda is because the Mazda stays there longer, so it's more power over time.
Okay.
So if all you care about as a detector is there energy in K-band that looks like ACW, this is going to set it off, even though you can look at this and say, this looks nothing like a police radar. And the key that I want you guys to understand is visually, literally with our eyes, me and you can tell that this is different than a Mazda BSM or a Falcon HR or whatever gun it is. That visual component's important because that's how Ray can see things, kind of like me and you do.
So let's take a look next at kind of continuous wave police radar. All right, and so next we've got a police radar gun over here. That's a what, custom Falcon HR?
Falcon HR, yep.
Okay, so tell me about this signal and what's going on here.
So before we even get to that, I want to ask you a question. Does this look like the BSM visually?
How many guesses do I get? Like, no, this is very different.
So what? Just name one different thing about it.
So one single big spike.
Yeah, exactly. It's a CW emitter. Do you see it spread back and forth all over here? No. Do you see it pausing, starting, No.
So it's continuous wave on one single fixed frequency.
Exactly. And this is why BSMs don't make sense to me, why this hasn't been done before.
Yeah,
because these look nothing alike. For some BSMs, you don't even need AI. For some, you do. But for other ones, you don't. And I just don't understand why this hasn't been done, to be honest with you, because you don't have to be a microwave engineer to look at this and see that it's drastically different than that Cadillac BSM.
Something else that was super impressive here, and I don't think you posted this on the forum yet, is like the fact that this is a police radar gun and it doesn't look like you have all these defining characteristics, but the AI is still able to tell this gun from another continuous wave radar gun.
Yeah, and that's something that is amazing. And one of the reasons that we have the CW gun discrimination here is almost just as like a demo to show how impressive the AI really is. Because to me and you, this doesn't have that many discriminating features.
It's a spike.
Especially if remember, we can't use things like amplitude to distinguish because amplitude changes when you're far away or closer.
Closer, it gets bigger.
So if you're just looking at actual emitter characteristics, there's not a ton here compared to the BSM because it's not modulated.
All you can look at is maybe the frequency the gun's transmitting on, but there's not much that we can see here.
So and this is part of our philosophy with the hardware design too. When we looked at this problem space, we knew what the dream was to get to the level where we could do CW discrimination or classification. And in order to do that, we have to have a super clean RF front end. Garbage in, garbage out. It doesn't matter how much AI I stack behind this or advanced technology. If the AI can't cleanly see the characteristics of an emitter, far better than even we can, it can't classify it, right? I mean, if you're blind, you can't tell which picture's which.
So basically, you're looking at this signal in extreme detail with really high quality components.
Extreme detail. Yep.
And so speaking of which, let's actually take a look over here at the next booth and show the next thing.
Sure.
That I wanted to show you guys. All right, and so next over here, you've got a booth set up where you can actually show that you're able to in real time like identify different radar guns, door openers, false alerts, anything like that. So let's actually can you shoot the Falcon HR? So you'll notice, boom, as soon as he shoots the Falcon HR, it says with 99% confidence, that's the Falcon HR. Here's what the gun looks like, and here's what the AI is actually seeing, right?
Yep.
So this is amazing, because like I didn't know you could do this level of classification with continuous wave radar.
Correct. People said that it was always impossible to do.
Yeah.
And on the surface, that makes sense why they would say that, because if you look at those signals like we did,
it's just a spike.
Exactly. But this is a visual representation of the data that the AI sees. So it's not technically seeing that picture, but this is a raster created from the binary data that we give it.
Gotcha.
And this thing right here in the middle is the carrier. And all of these little things here are subtle variations in the beam width of the CW signal. So that is the difference between these signals that it can see.
Can you also shoot like maybe the Talon next? Okay, cool. So it's able to do the Talon. Can you do like the B3? Okay, cool. So yeah, and it can ID the B3. So basically you're able to do all these different guns, like, and this doesn't look at the frequency, right? I know this is 33A.
Frequency has nothing to do with it.
Nothing to do with it.
Yep.
So how is the AI actually telling the difference between these guns?
Because there's subtle variations in each of those little rasters, I guess you could say. And this comes down to some of the hardware advancements that we made. I think over on our booth, you saw the term phase view. This is the only radar detector on the market that can see something called phase. I'm going to skip the technical details of what phase is, but long story short, we can actually see 50% more information contained in an equivalent signal than any other radar detector. And because we can look at a signal in different ways, not just from one way, that means that we can see things that can discriminate the emitters that other guns or other detectors simply can't.
Yeah, that's awesome.
Yeah, it's really cool.
So you've also got door openers marked here.
Yep.
Tell me about this.
So a door opener is just a CW signal. It's no different than any radar gun. So you can see here that the raster kind of looks the same to you, and while we struggle picking out patterns, to the AI, that's nothing.
So what are you able to do if you can uniquely classify door openers? Like, how does this make it different for us as radar detector users?
The more certainty that a radar detector has that a signal is one that you want to hear or you don't want to hear, the better the user's quality of life is, so to speak. And the cool thing about what we're doing and everything being software defined and us doing everything in-house is that I really don't have a problem with allowing the user to choose. If the user, I personally don't want to hear every Cadillac going down the road, but some people might say, I would like to know there's 6 Cadillacs near me. I really don't see a problem in just letting the user have that freedom to choose. Do you want CW discrimination? Do you not want CW discrimination? Do you want to see the BSMs? Do you not want to? This is a AI-powered edge inferencing radar detector classifier, and I want to give people the tools to play with that through an open API, maybe even open sourcing some stuff down the road. This is a community-driven project from the beginning. I don't see a reason to pull back from that now. This is a whole new level of knobs and levers that we can give people to learn about their RF environment and play with.
And this changes things, because if you can just tell that's a door opener, then you no longer need low-speed muting or GPS lockouts to filter those out. You just don't alert.
So I think the biggest thing to touch on is related to filtering, like TS reject, K narrow, auto city mode that we have. Those especially are simply no longer necessary. All radar detectors are artificially holding back their sensitivity. Even the legacy detectors, as I call them, everything not an AI is a legacy detector to me. Those all have a level of filtering that you can't disable just because they'd constantly be going crazy. We don't have that. So even if our hardware wasn't any better, we're already picking up multiple decibels of equivalent sensitivity just because we don't have to hold back the hardware.
And it's different, so if you're able to just tell, hey, this is a Decatur gun, this is a Falcon HR, do you really need BSM filtering, or can you just say maybe just train on radar guns, or how would this work?
There's multiple ways that you can do it. You could do inclusive filtering, which just says only alert to something that passes a certain threshold of a class we trained. So I could train this to say, I only want to know Decaturs, don't alert to anything else. Or you could do it the other way. I mean, there's a million ways to do this, and the powerful thing about it is that because data collection and training is so fast, it allows us to record, train, test. Record, train, test.
How long does that take?
I can record about 60 seconds of data from a gun, which is all that I need for basic level discrimination. Transfer it onto a flash drive or put it on the network. The supercomputer right now with our current model, which is not done, we don't have every emitter trained yet, takes like 15 minutes to get to very good accuracy. And then we can test. So it's compressed this process of which used to take 2 months of development time, filter development, algorithm development, and it compresses it to this 2 or 3 hour span where during the course of a day, we can develop and test multiple 0 to 100 filters. The speed of development is just mind-boggling in what it's enabled us to do.
So like if a new car comes out with a new BSM or a new radar gun comes out or something, you can just record it, train?
Same day.
Done.
Same day.
That's nuts. Other manufacturers, I know they have to like sit here and try to write the code and develop an algorithm to filter this new BSM or something, which takes time.
Yep.
It's tough, and you can just got it, boom, done.
Yeah, I mean, there is no emitter currently that we haven't found any emitter that we can't train on successfully, whether that's CW or BSM, and the time is the same for all of them. It's just train the network.
So is this what we're looking at? Is this like just a demo for the show, or is this running on an actual radar detector, or what is this?
So this is actually running on our production radar detector hardware. This is our production horn, our production circuitry, and it's running on the exact same single board computer, or SBC as we call it. That's that module where the AI lives and does everything, as our production radar detector will be. Now, this particular GUI or graphical user interface, yeah, we designed this for the show just to make it easier for us to stand here and point at, but this is totally possible to have on our actual detector. So it just won't be 4K.
So it's basically a production radar detector with a different display. It's not the little LCD, it's just outputting to a monitor.
Yes, and as far as the performance goes, this is not fudged in terms of latency, inferencing time. I don't mind publishing the specs. I mean, right now it takes us about 12 milliseconds to successfully inference on our production hardware.
That's super quick.
Yeah, it's really fast.
Quick. So now over here next to the setup, I see we actually have, it looks like a radar detector with 2 antennas.
Yep.
So what is this here that we're looking at?
So we actually split this apart because I think it's easy to understand how different parts of the detector serve different functions, exactly like it will in the production unit. So this right here is actually our production horn. This is done. And the circuitry inside that is our production circuitry. A little tidbit I can say is that we are using 4 LNAs inside, which is pretty cool. It's 1 dedicated X band and 1 dedicated K and KA per horn.
Per horn.
Yep.
So 2 horns, arrows as well.
Exactly. And the other thing that I can say is this is a really unique design because it is not a multiple stage mixing front end. We said the simpler the better, so we could use extremely high power, high quality components. Now that wouldn't really work if we did a triple mixing stage, for example, because there's more components. Each time you go through that, you lose a little bit, or you can introduce distortion. There's more to go wrong. And with an old-fashioned detector that doesn't have this kind of processing power, you can't deal with imaging problems that stem from this simple design or filter problems that stem from this design. But because this is a software-defined radio, all we care about is having the cleanest possible signal come from here, and this can just take care of everything behind the scenes.
So this is the computer essentially that's processing everything.
Yep, so for the course of this demo, we have everything hooked up to this. This is where Ray lives, artificial intelligence. But the actual detector uses this. And this is kind of related to one of my RD form hints Click was about. This detector, or this computer right here, is actually an entire Linux computer. It's a quad core, 1.5 gigahertz. It has DDR memory, and it has 8 gigabytes of flash storage. So this is kind of similar to what your cell phone is, but it lives on this little SODIMM, they call it, or it's a computer on a stick.
So it's basically a computer that you're running.
Yeah, that is the exact same as this. This one just has the ports, that one doesn't. It's a different form factor.
Yeah.
But we are putting a Linux computer on a radar detector. That is actually what this is.
So this is going to be, as you said, far more powerful than just a simple radar detector with embedded hardware. Like,
correct.
This is much more capable.
Exactly. And the cool thing is just like when you get a new Mac or a new PC, OS X or Windows doesn't really care like the details about the tech specs behind it. The software runs the same. That's how we built this as well. So over time, in 2 or 3 years, or whenever we release the next generation, processing speed increases, right? Our code is just drops right in and runs. We've kind of created a countermeasures operating system, similar to Windows or Mac OS X.
And so I know you mentioned on the forum too, this is modular, so you could drop in a new CPU, you could put a different horn, you could change the components without having to completely redesign the detector from scratch.
So on a legacy radar detector, if you want to change sensitivity, you have to actually change physical components on the board. With this, it's just ones and zeros. I can actually increase gain on a software level, and that's just one example of what we could do. If you want to receive satellite communications, our artificial intelligence and the actual CPU is totally capable of doing that. You would need a different horn, a different antenna, so to speak, but this is really not just a radar detector. It's a radio frequency communications platform. It's really neat.
That just happens to be set up to detect police radar guns.
Exactly. So internal to the horn, we do have bandpass filters that say, hey, we mostly care about X, K, and KA. But if we change that, the back-end hardware is totally compatible with whatever we decided to do.
And this is also capable of detecting like the MRCD, MRCT, gap
all of
fill,
that.
all that too, right?
Adding support for any camera class in the world, whether it's Mesta Fusion or MRCD or MRCT, is exactly the same as training out of BSM. Take a recording, give it to Ray, press train, and she gets it right.
And then she shouldn't have the same issues with false alerts like we see with other MRCD capable detectors.
Yep. The reason other detectors false alert to MRCT and MRCD is because they can't really see the signal as clearly as we can. They know it's pulsed, they know it's not CW, but as I showed you, BSMs are pulsed too.
Right.
So they get confused between BSMs and the various types of pulsed camera systems.
That makes sense.
Yep. But we don't have that problem.
What about maybe other aspects of the radar detector besides like it's got arrows and all this? What about the range? What are you anticipating?
It will be significantly more sensitive than any other detector in the world.
Significantly more sensitive.
Yes.
So even everything else currently on the market.
Yeah, I'm not prepared to give exact decibel figures yet, but it's
still in development.
It's significantly more sensitive than any other radar detector.
So I know one of the biggest advantages of long range is not just 10 miles or 20 miles of range or whatever, but it's also detecting instant on at a distance before you get to it.
Yep.
And I know you've got something kind of unique here specifically for instant on too.
Yeah. So instant on, as most of you probably know, is probably I would say maybe the greatest threat that radar presents to a driver.
Yeah.
And it's especially deadly because at long distance, it's difficult to determine whether you're getting a weak sniff of a false alert or actual instant on, right? What we discovered is that we can see the signal in such extreme detail that we can see transients or frequency drift when the trigger is actually pulled. These happen in terms of microseconds to milliseconds, but we sweep fast enough where we can capture these, and turns out each gun has a unique signature when it does that. So I mentioned earlier that when somebody pulls the trigger on a gun, it does emit a signature that's different than that of a gun that's been on for a long time. And the reason for that is actually temperature. Radar guns are analog devices. When you pull the trigger, you send electricity into the radar emitter. That emitter heats up. And as we know from our experience in the radar detector world, sometimes you see frequency drift when it's cold or hot, right? The same thing happens for these guns. So it's hard to see fast here, but it's also kind of cool that we can pick it up even though how fast it is. The first thing we want to do is look down here. When the trigger is pulled, you're going to see it's almost like a Nike swoosh that goes up. You can also see that up here, how it doesn't end right here, but it starts over here and slides. What you are seeing is actually the emitter changing temperature in real time.
And then that temperature change leads to a frequency change.
Exactly. And this is the case for every gun. And what's cool is that every gun of the same design has the same frequency shift, but that's different than a different brand gun or a gun of a different design.
Okay.
So just like we can train to tell the difference between a door opener and a Detector gun, for example, what we can do for training is just take a bunch of those, a bunch of the images of the swoosh, so to speak, and just give that to Ray. And Ray says, oh, that is a trigger pull signature that is different than a CW signature.
So CW would just be fixed frequency. Can you hold the trigger down?
Yeah, so I would take a recording of this, label it CW fixed, and then I would take a recording of just the swoosh, label it IO, and train on that. And you taught her. Every time she sees the instability, she'll call it instant on. Every time she sees the CW stability, she knows it's not.
So this would be super useful with a detector that has crazy sensitivity, obscene range, I know is how you wrote it.
Exactly.
So you can now tell, boom, that was an instant on or a quick trigger shot at a distance. Even if the signal disappears, you still get that
Exactly. Alert. Is it absolutely necessary? No, but it's another level of situational awareness, which is really what we're all trying to go for with these devices.
There's so much that it's able to tell you, classifying the guns, instant on versus constant on, false alert versus legitimate. I mean, there's just so many things that you're able to tell that we haven't been able to know before.
It's a different type of device. It's a modern device. It's an iPhone versus a flip phone.
Yeah. So, okay, so this looks awesome, obviously. What's the kind of expected price point and release date for us to be able to get a detector like this?
So it's going to be a premium expensive detector. You know, this is not going to be a $299 detector, but it's not going to be that far out of the range of a typical premium high-end dual horn detector. So, you know, unfortunately, the first one, we want to make a statement that we want to have features like arrows using these high quality components. One kind of interesting thing is that there are numerous single components on that board that cost a significant portion of the entire build cost of other radar detectors. I mean, you guys can go Google and look up what I'm paying for that computer. It's publicly out there. So it's not going to be cheap, but I want this to be something that an enthusiast can afford to get and play with. So we're going to do our best.
What about expected availability?
It's going to be next year, so nothing is going to ship. I've tried to be pretty consistent on the forums. One of the reasons that we're showing this so early is just because there is so much education that needs to be done ahead of time. So I want everybody to really understand the ins and the outs of how we're doing things, and as you said, it's just a different method. So I think it's cool to show it early to give people time to talk and learn.
There's so many fundamental shifts of like, wait, you don't need GPS lockouts. You technically don't even need to train for BSMs if you don't want to. Like, you don't need TSR, you don't need K-narrow. Like, there's just so many basic shifts and things that are done differently here.
Yep, and I intend to be fairly open and engage the community in talking about this as we continue to learn. As I said, this is kind of a community-driven thing. It doesn't really make sense to put as much money into development for a radar detector as we've done.
But thank you for
But
doing this.
it's really cool, and all of us are pretty excited by what we've managed to accomplish.
Totally. So I've been spending the day here pretty much just learning. This morning I sat for a couple hours,
Yeah.
so just talking with Radenso's engineers, learning how all this stuff works. And so I want to do over the course of this week, sit down and do another series of videos talking about how the neural networks and the AI works and all these cool little things that we didn't talk about here. Plus, I want to hear from you guys. If you have any questions, whether you're on the forums or YouTube or wherever, ask me, and then maybe by the end of SEMA, we can sit down together and talk about some of the most frequently asked questions.
Totally.
Okay. Awesome. Well, thank you.
Thank you, guys. I appreciate it.
Yeah.